G'day, Dr. Carl, Shirtloads of Science, and today we have, is the phrase a friend of the show?
Yeah, why not? That'll do.
Professor Geraint Lewis, did I get the pronunciation correct-ish?
Better every time, Carl.
Okay, and today the big mystery, the onion layers of a supernova. So a supernova is a star that explodes, is that right?
Yes.
Okay, and there's two different types, and we're not going to look at the type where you've got a type 1A where you've got a white dwarf next to another star, and we're going to look at the one where it starts off, it's really big.
Yes.
It's a big, how big does it have to be in terms of stellar mass compared to the sun?
Well, the more massive you make the star, the more violently it can explode. So you can get supernova probably around, I think, about 8 to 10 times the mass of the sun.
That's kind of where it begins-ish.
Yeah, but there are much heavier stars out there. So, you know, 50, 60, 100 times the mass of the sun. The bigger you go, the more potential there is for a bigger explosion.
So Carl Sagan said we're all made of star stuff, and that the heavier elements, other people have said the heavier elements are made in stars and released when they explode, and that makes us. But they were thinking that there's an onion layer type thing, that you have the hydrogen fusing to helium, and that gives off energy. Then that helium acts as the next stage to make heavier elements, and they talk about different layers such as helium, carbon / oxygen, and then as you keep on burning your way up to heavier elements, at each stage you get less energy, and then you go oxygen, nitrogen, neon, magnesium, and then oxygen, silicon, sulfur, and then iron. And they're saying something about they've seen the onion layers.
Okay.
Can you turn this into English?
Okay, let's take a step back and imagine a newly born massive star.
Newly born massive star.
So,
gotcha.
yeah, take a big gas cloud,
Yep.
and take a big chunk of that gas cloud, let's say 60 times the mass of the sun, and allow it to collapse.
Right.
Now, most of the gas in the universe is hydrogen and helium. It's the stuff that came out of the Big Bang.
And that's 90%, 10% when the Big Bang happened, things cool down. So, and a bit of other stuff,
Yeah. So that gas cloud, gravity grabs hold of it and it starts to collapse in on itself, and eventually, right, it squeezes down. The temperature of the gas in the middle starts to rise, and it rises rapidly. You've pumped up a bike tire, Carl, and you know that if you compress gas, it gets hotter, right?
And in this case, the number is 15 million, roughly-ish?
It's into the millions of degrees. Into the millions of degrees.
You're an astronomer, so...
Yeah.
Or a factor of 10 either way.
Yeah. So you squeeze the core, and you get to the point where essentially the hydrogen and the helium, mainly the hydrogen, those atoms are close enough together and they're flying around so fast that they start to collide, and you start to get nuclear fusion.
Okay, so the cores of the atom, so we're not talking chemical reactions with the electrons, we're talking the nuclei. So a nucleus of hydrogen, another nucleus of hydrogen gives you some version of helium and a lot of energy?
A bit of energy. A bit of energy. Each one of these things releases a bit of energy, but there's so many of these reactions going on that the total amount of energy in the core, you're talking about masses again, like the mass of the sun, of hydrogen and helium basically starting to burn. That energy then starts to flow outwards, and that's when our baby star really becomes a star, when it starts to get that nuclear fusion in its core. Right? Now, the rate at which a nuclear fusion runs is dependent upon the density and the temperature.
Okay, how many atoms you've got there to fuse, and the higher the temperature, the more rapidly the reactions will happen. Okay, yep.
And both those things depend upon how much gravity is squeezed in the core.
Right.
So if we go to the other end of the scale and we look at a red dwarf star, which is a tenth the mass of the sun.
A tenth of the mass of the sun, and just heavy enough to do nuclear fusion.
Yeah.
It's just over that.
Just over.
Just able to do it, yeah.
It has its nuclear reactions, but they're bubbling along, and they bubble along for a trillion years. But inside these massive stars, it's so hot and it's so dense that all that hydrogen and the helium get rapidly used up. Okay, so basically you can imagine the core becomes helium first. And then essentially once the core's all helium, the star basically runs out of that energy which is flowing outwards. And so gravity squeezes a bit harder. The density and temperature goes up.
Gravity, so you've got the nuclear fires pushing out and gravity pulling in.
Yeah.
So temporarily the outward force is a bit less, so the force of gravity overrides the push outwards,
Yep. And so what happens then is you get to the next stage where you burn like helium into carbon, and then oxygen. So you go through these stages, right? So in the core, you'll get to a point, it'll use up all the fuel, you get a bit shrinking, ignites again, uses up the fuel, etc. But what's really cool about these massive stars is that in that squeezing, right? So imagine that firstly, you've got the core and you've burnt all the hydrogen into helium. So you've got a helium core, okay? So you then start to squeeze, and in the helium core, helium starts to fuse into carbon. But just outside
that's the next one up, is it?
Next one up, yes.
You ignore the lithium and the boron for various reasons.
Yeah, let's not...
Don't
worry about it.
Yeah, don't worry about it.
But if you imagine, right, so we were talking about hydrogen burning to helium in the core.
Yep.
Outside of the core, there's still hydrogen. But you've now started to squeeze that region outside. So outside the core, hydrogen starts burning into helium. So you get
it reignites it.
So you've got fresh raw material, but you've given it an extra squeeze and you've taken it over that line where it can start to fuse.
Oh, so the brightness, the energy output drops, then comes back up again?
Yep. Oh, well,
really?
and it varies. Stars tend to settle down into stable situations, so there will be a balance between the outward push and the inward squeeze. And it goes on like this. So imagine that you burn the core, all the core is burnt into carbon, right? Outside the core, there's a shell that's all basically burnt into helium, and outside that, you've got hydrogen.
Right.
So once you get...
So like onion layers.
Start to building up onion layers.
Right.
So then you get another squeeze, and inside the core, carbon gets burnt into oxygen, right? Outside the core, you get helium now being burnt into carbon, and outside that, you've got another fresh layer of hydrogen burning into helium. So over time, you quickly build up these onion layers. Well, I would say quickly, because the rates of the reactions are getting faster and faster because you're squeezing the core more and more. So that initial stage of hydrogen to helium, that might fuel the star for, I don't know, let's say 10 million years, which is nothing in the lifetime of a star, right? Our sun is already 5 billion years old. So 10 million years, it's your James Dean of stars, right? Living fast, dying young.
Okay, so ours is living slower, and it's going to go for a total of 10 billion before it does this thing at the end.
Yeah.
Okay.
But then the rate at which the core burns this material to higher and higher elements gets shorter and shorter. So it goes from millions of years, hundreds of thousands of years, thousands of years, hundreds of years, less than a year, until you get to the last stage. And the last stage is when you get to, I think it's, I'm going to look at my picture here. Look, I think it's when you get to silicon, right?
Oh, silicon is the atom before iron.
Iron, yes. Yeah, imagine that you get to this point where the core is now silicon, and then you work your way outwards. You're going to get like silicon and oxygen layers, etc., all going outwards. Silicon gets to that silicon stage, and again, another squeeze, silicon starts burning into iron. Right?
And we're talking nuclear burning, just to be clear, not chemical burning with electrons.
No,
forget the electrons.
Nuclear burning.
We're in the nucleus here.
Yeah.
This is nuclear. Yep.
Right. It burns through all of that massive silicon in one day.
What?
The reactions are so vigorous, right? One day, all of the silicon gets fused into iron.
So this is several times the mass of the Earth of silicon, I'm guessing.
Probably might be a couple of times the mass of the sun.
Of our sun?
Yeah.
Oh, wow. Okay.
Yeah. Yep. So it all goes very, very quickly, right? And then suddenly, bang, nuclear fusion turns off in the core.
Nuclear fusion is turned off because you've turned the silicon into iron, which, as I now know, has the highest binding energy per nucleon, nucleon being a proton or a neutron. Look it up on Wikipedia. Yep. And then?
So if you want iron to fuse into heavier elements, you need to put energy in. Right, so it's unlike all of the other reactions, which are exothermic, they release energy.
They give off energy.
If you want to fuse hydrogen, because it's got this really tightly bound nucleus, you need to put energy in. Okay, but there's no energy going in. Right, all the energy was being produced by nuclear fusion.
We've taken the potential nuclear energy out of the nuclei.
Yeah.
So the nuclear force. Is it strong or weak nuclear force?
Both play a part.
So both the nuclear forces are no longer available as a source of energy.
Yep.
Now, I do know there's another force in the universe, the electromagnetic force. Forget that one.
It's there, but it's not producing energy. Things are bouncing around, but it's not producing any energy.
So that leaves us with...
Gravity.
Really?
Right.
But gravity apparently is the weakest force?
It's a very weak force, but I don't have to tell you, even though it's a weak force, if you jumped off a building, it would hurt, right?
Yep.
So if you accumulate a lot of mass, gravity can do a lot of things. So what happens is that you turn off that nuclear fire.
You turn off the nuclear fire, there's no outward push,
No
more.
outward push, so the outer parts of the star move inwards, right?
They move?
Yeah, the star...
Physically?
The star collapses.
The star collapses?
Yeah.
What happens to the atoms? Do they get mushed up hard against each other?
No, that's precisely right. So imagine now that gravity comes, pulling all this mass in, it smashes down on the core, right?
And so in each atom, you've got a cloud of electrons saying to the next atom, keep away. That's the electromagnetic force. And the gravity force, because there's so much gravity, is able to overcome that and push the atoms closer together?
The electrons aren't bound to atoms. It's so hot.
It's a plasma.
It's a plasma, yeah.
Okay, right.
But the nuclei, which are positively charged, they want to repel.
Yep.
But gravity comes in, smashes everything. Things get forced together.
Wow.
So if you get elements heavier than iron,
yep,
they were created in these really violent events where you could squeeze the nuclei together, right?
Right.
So, but remember, I told you that the rate of a nuclear reaction depends upon the density and temperature.
Density and temperature, I remember that.
And what you've done is you've squeezed the core now. The temperature goes through the roof. The density goes through the roof. The nuclear reactions that you are fueling via gravity basically release this huge amount of energy.
So you've got the energy coming from gravitational energy, which then gets turned into
basically new energy being released through you force in nuclear fusion of iron to heavier elements.
So that's where the lighter elements up to iron, number 26 or whatever it is,
yeah,
they get made in a normal burning of a star.
Yeah.
And then the heavier elements get manufactured. Well, one source of manufacture is inside supernovas, you're saying?
Yes. So you forge heavier elements, and there is energy released, but it's a very messy situation. So firstly, imagine the outer layers crash down.
Yep.
They basically bounce off the core, and they then spread outwards. That's your spreading explosion in your supernova. Right? But the nuclear reactions where you forcing things together produces all of these little neutrinos, these little ghostly particles, which travel through you and me and everything else.
Hundreds of billions per
but
second.
there are so many of them here, right, that they help lift the entire layers off the star.
Really? So my understanding was that neutrinos interact so little with regular matter that you'd need, I've heard the figure, a light year or more of lead to have a 50% chance of stopping a neutrino. And here you're saying that over a distance much less than a light year, like a light minute or a few light seconds, there's so many neutrinos they're able to push.
Well, there's two things, right? Number one, there's so many neutrinos.
There's so many neutrinos.
There's so many.
Absolute shirtload of
Number
neutrinos.
two, the material is much denser than lead.
Oh, the material is denser than lead.
Yeah, it's nuclear material, right?
Okay, so forget an atom here and an atom there. You got the nuclei mushed up hard against each other. The nuclei.
Yeah.
Forget the electron clouds. The nuclei. Wow, that's really dense.
So then the outer layers get ripped off and they head off, and that's when we start to see this brightening of the supernova. So essentially, the star is ripping itself apart.
Why do we see the brightening? Why does it? Because it's hot and it's giving out the stuff in the light band, the 400 to 700 nanometer blue to red visible band.
All that energy that was inside the star is now thrown out, right? So essentially the star rips itself apart,
Yep.
right? And that's what we see as this supernova explosion, right? The core itself, right, might be left over and has been crushed down either into a neutron star, which is essentially a star with the same density as an atomic nucleus, right? So
really?
So if you try to stand on the surface, you would rapidly become one atom tall, but
the
very,
gravity
very
is so strong.
Yeah, but very, very broad.
Wow.
But the temperature of that neutron star will be like millions of degrees. So you would fry. Yeah, it's still really, really hot. They cool down over time, but they're still very hot.
So a neutron star, a couple of times the mass of the sun, and maybe 20 kilometres-ish, ballpark figure?
Size of Sydney, that's a handy sort of size you can use.
But it's the density of a nucleus.
Yeah.
So that's one pathway or one terminal result for a star going supernova, and the other one is?
You could completely crush that neutron star out of existence into a black hole.
Where it has zero size. which is something that still hurts my head. And when I remember you corrected one of my stories once, and you pointed out that it had zero size. And even though I wrote down your correction, I didn't believe it. And then a few years later, I had to run it past you again. It's hard for people to appreciate that something 5 to 50 billion times the mass of the sun has zero volume, not just a small size, but zero size.
Yep.
We're talking the singularity, not the event horizon.
Yeah, that's right. So all the mass gets crushed down, well, essentially crushed out of existence, you would say, right? When it's in the singularity, whatever that means.
Whatever that means.
Right, it's in a volume with zero volume, right?
And is singularity a physics term, meaning our equations don't work no more, we don't know?
A singularity is a mathematical term. It just means things basically blow up to infinity, and we don't know what to do when they do that.
So you need different mathematics or something?
We're still working on that one. What does a singularity mean in the middle of a black hole? But in our current theory, which is Einstein's general theory of relativity, there's a singularity at the middle of a black hole. Maybe quantum magic comes into play when things get very, very small and might prevent it going to infinity. But at the moment, nobody really knows.
Right. So getting back to this New York Times headline, so it says, onionlike, holding it up here, onionlike space explosion may be a new type of supernova. And they were talking about it happening over periods of thousands of years, the layers being pushed apart. I think they were talking about a silicon layer. Now, where do I underline this here? So the outer layers made of lighter elements like hydrogen and helium give way to increasingly heavier chemicals like carbon, oxygen, magnesium, silicon, sulfur, argon, and finally iron at the core. And they observed the moment when the star's iron core exploded, lighting up a previously expelled stellar layer which was rich in silicon, sulfur, and argon.
Let me explain.
Yeah. So apparently that to get to where it was, it must have happened thousands of years earlier or something. I don't know. Help me, Professor G.
Okay. Do you know how our sun is going to end its life?
I'm guessing our sun is going to get part of the way down a red giant, definitely swallow up Mercury, possibly Venus, maybe Earth, don't know about Mars, then shrink down to 100 times smaller than it is today, called a white dwarf.
You missed an important part there, right? So again, the sun is quite massive, but it's a small star.
Yep.
So it can do the hydrogen to helium burning, but it can't really go much further than that. So as you said, it gets to a point where it's run out of hydrogen in its core, and it has helium, and it starts to burn helium, but it never will have enough gravity to really squeeze the core and burn into heavier elements. Now,
really? Our sun will not get past helium?
No, it will build up carbon. It will burn
get
carbon, but it won't get really beyond carbon.
It won't get to silicon and...
No, and nowhere will it get to iron, right?
Okay.
So its destiny is not the same as these massive stars.
Right.
Now, when it goes through that change of burning hydrogen to helium and then helium to carbon, there's a change in the makeup of the sun, right? As I mentioned, it goes through this hiccup where it has to rearrange itself to give you a bit more squeeze in to burn the hydrogen to helium. But for a star like the sun, when it gets to that old age kind of thing where it's now doing its helium burning, it sort of becomes cantankerous. So it doesn't settle down to balance gravity versus the outward push of radiation. But it goes through these stages of sometimes gravity wins and it squeezes harder. Then that releases more radiation, so radiation pushes outwards. But then that nuclear reactor turns off again when the squeezing drops, and it goes through these cycles. And the outer layers of the sun will eventually basically be blown away, right, in what's known as a planetary nebula. So you must have seen pictures of planetary nebula.
And they're beautiful.
They tend to be beautiful. You tend to have a little dead star in the middle, and you've got this expanding cloud, which used to be the outer atmosphere of that star, spreading out into space.
Right.
Okay? That's how some of the elements that we are made of got from the center of the star out into the gas and then eventually cycled into us.
So we are, 60% of our atoms are oxygen. And so Carl Sagan was right when he said we are star stuff.
Yeah, but then again, so are cockroaches.
True. Yeah, but then on the other hand, hydrogen is not star stuff. It was there before
it was
the star.
made in the Big Bang.
Okay, so we just got to be clear about that.
Yeah. So that's the destiny for the sun. Now, in these massive stars, when they, I said, they already go through these hiccups, okay? And we think we understand the physics of what's going on in a massive star, but they're complicated beasts, right? in 3 dimensions, they might be rotating. They probably are rotating. They might have a companion star that's going to interact with them and all that kind of thing. So they will also have their own kinds of hiccups, right? And what this paper is suggesting is that something, right? Maybe this underwent some big hiccup in the past, which instead of just making the star expand and contract, but actually managed to detach some of the outer material and flung it off into space. Right? So it was already expanding away from the star. So it had gone through some sort of violent interaction. That material is out there, but then when the star goes supernova, that material gets lit up again.
It gets lit up, so it's there, but we can't see it with our telescopes because it's not giving off electromagnetic radiation, or light, as you astronomers call it.
Yeah.
And only when the central bit goes bang, does that then throw photons of light, which then bounce off that, and then we can see it with our telescopes?
Yeah, bounce off. So there will be physical interactions.
So not bounce off, get absorbed and then re-emitted?
Well, some will bounce, some will interact with it, etc. So if you want to reveal the chemical signature, that light has to interact with the atoms there, right? Because you're looking for spectral lines. But we can see this in the Large Magellanic Cloud. Back in 1987, there was a supernova there, and we can see gas and dust that has been lit up by the supernova that surrounds it, right? And it's kind of a complicated structure that's being lit up. It's not like a nice spherical ball of stuff. It's more complicated. So maybe that's what's happened here. There's been a more complicated interaction that has thrown off material that you wouldn't expect if the star was just going through something nice and simple. So, but what they're seeing in this, of course, is that material must have come from deep down in the star and has been thrown out and appears to reflect this picture of onion layers that you were talking about. That the mass is distributed in layers where in this layer, silicon dominates, in this layer, helium dominates, etc. So essentially, we are looking inside of a star, which is difficult to do in a supernova because it's like trying to look inside a nuclear weapon after the explosion. Right? There's not much that you can pick apart to tell you what the nuclear weapon looked like. This is what we've got here. Once a star explodes and rips itself apart, it's very hard to say, what was it like before it blew itself apart?
So this paper was extremely stripped supernova. So that means it's thrown off some of its onion layers, reveals a silicon and sulfur formation site. So the core is that the radiation they're getting off from the center of the supernova?
So this will be material that was deep down in the star.
It was deep down.
But has now been thrown out and has been lit up by the supernova. So we know that material, again, that star when it formed was hydrogen and helium. Right?
And with 60 times the mass of our sun.
Yeah. But now when we look at the light that we see from this star, we're seeing silicon and sulfur, right? So those signatures have come from the middle of that star.
And physically being shifted out to there by outward pressure.
After the explosion, the state of stuff around a supernova is a real mess because you create elements that start to undergo radioactive decay. So you start to see signatures of cobalt and all these different kind of things which tend to swamp a lot of the signal. But what they're saying here is that what we're really seeing is some of the air quotes pristine, right? So the pre-explosion material because it was thrown out and then lit up by the supernova.
Right, and obviously we don't have a real photograph from the telescope, but there's a nice artist drawing showing a nice, beautiful sphere. So from what you've told me, it could well be spherical, but it's almost certainly bumpy and it might be oval or God knows what.
The people that study supernova explosions, they have to study them on supercomputers, right? Because you're doing this explosion which takes place over a fraction of a second and tears a star apart, right?
Wow!
But if you can YouTube this, you can look up supernova explosion and simulation. You can see the explosions, and one thing they are not is nice and spherical.
Really?
Now, the star basically, you just imagine it, right? It's an explosion that's taken place, and it's not going to be a uniform explosion. Stuff's going to go off that way and that way. So it is a messy thing, and it's a messy thing to try and study.
Okay, now is it fair to say that this study here is important because it gives a hint of the star's layered structure, comma, something never seen before. Is that correct? This is the first time we've actually seen evidence of this onion layer, or do we have other evidence of it that's not visible?
Well, evidence is it's not a single thing, right? So we can have an idea from the distribution of elements in the universe about which ones are produced in supernova and produced in massive stars, and that seems to work. The important thing here is that they are seeing silicon and sulfur together, and in the onion layer picture, they should be near each other in the star, right? Because it's not like it's made of hydrogen and iron, which would be weird because they are from very different locations in the star. So these seem to be from a nearby in the star. So it looks like something has grabbed a chunk of star, ripped it out and spread it out through space, whatever that process was.
Yep.
But it's consistent with there being the two layers of the star together. Let me put it this way, right? Imagine that I scooped up some chunk of the Earth and gave it to you. And if it was water and oceanic crust, you sort of go, yeah, that came from like a similar kind of region, right? But if I give you like seawater and a bit of the core, and I said, oh, some process threw these out, you'd be like, but seawater's from a very different location on the planet to the core.
6,000 kilometres different.
How would I find them together? Right? You'd have to contrive a picture to get a piece of core and a piece of seawater together in some sort of random kind of thing. What they're saying here, of course, is that silicon and sulfur close together, right?
It fits.
It fits.
Okay. Now, the whole thing that started this off was my inadequacy, where a student, a primary school student, because I do these regular science Q&As on Wednesday afternoon, said, how does a supernova work and how does it get its energy? And I suddenly realised that I had a really messed up thinking that was built up of bits and pieces over the years. Can you, for that student and me, give me, here's a question without notice, like a 1 or 2 minute answer that I could then give to I could plagiarise and pass off as my own work to the next student who asked me how a supernova gets its energy. So, Professor Dr. Geraint, how does a supernova get its energy?
The answer is gravity. It's essentially gravity driven. So when that iron core turns off, it can't produce any more energy. The only other source of energy is from gravity. So that all that mass out there starts to accelerate inwards. In the same way as if you jumped off this table and you would accelerate into the floor, the higher you jump, the more energy you're going to hit the ground with. Now imagine, effectively, almost 60 solar masses falling the radius of a star and then crashing down. Okay?
Crashing onto something how big?
10,000 kilometers. Not much,
like the Earth or something.
Earth or something, yeah.
Yeah, okay.
That energy, and again, firstly, you get two effects. Number one is like if you take a power ball and you bounce it on the floor, right? So you throw it downwards, it bounces upwards, right? That's part of what happens. There's a bounce that turns that fall inwards into outward motion. Now, you might say, oh, but doesn't that just mean that it bounces back to where it got to? But in that collapse, right, we've still got those other onion layers.
More energy. So it doesn't bounce to where it got to, it bounces more.
Yeah, because you put energy in from a little bit, well, not a little, it's a lot of extra fusion because you still have material that can fuse when you drive the temperature and density high enough. So it goes bang, and then you get all the extra energy which rips the star apart.
I shall plagiarise that. Look, thank you so much, Geraint, for coming in and setting me straight on. So I had it wrong all those years when I was saying that iron had the lowest binding energy per nucleus. It's got the highest.
Highest is the most stable. It and nickel are the most stable nuclei.
Oh, and nickel.
Yeah, they're very close. There's a bit of an argument about which is the most stable, right? But they're very close to each other.
Thank you for setting me straight, and I look forward to learning more from you next time.
Thank you.
Shirtloads of Science is washed, spun and aired by the University of Sydney.